Hello, Abia. Can you hear me?
Hi, Dr. Abia. Yes, I can hear you.
Um, would you mind
Uh,
share your screen?
um,
So there's a button at the bottom. You see that green button at the bottom, and if you click that, and then should pop up saying share
okay.
your screen.
Yes. Let
And
me.
then if you can bring up your slides, then we should be able to see that.
Okay. All right. Let me do that. Right. Um. Just a moment. Can you see the slide now?
Yes, we can. Yes, we can see the slides now.
Okay.
I still need to work out the audio because your voice is not through my own computer, and the
Mm,
other students can't hear that very well. So I
okay.
need to bring your audio to the multimedia here.
All right.
Give me a few seconds.
Okay.
Can you please say something?
Um. Definitely, everyone. Can you hear me? Hello. Are you there?
I can't remember what I did the last time here. Always muted. Can you say something? Okay.
Good afternoon, everyone. Hello. Hello. is mute. Dr. Abia, can you hear me?
Hey, Abia, I think you are muted now.
Yeah, can you hear me now? Can
Hear
everybody?
you now. Okay, I see you unmuted. Can you say something?
Yeah. Good afternoon, everyone.
Yes, you can go ahead with your presentation.
All right. Okay. So, good afternoon, everyone. I hope everyone can hear me. My name is Abia Katimbo, and I'm here at West Central Research and Extension Center in West Park. So, I'm going to present a paper that is about the research that focused on using deep learning for image-based plant disease detection. And it was done by Mohati, Hughes, and Balansi, and this paper was published in Frontiers in plant science. So let's just go straight to the introduction. We all know that crop diseases are a major threat to food security because of network infrastructure that is able to detect and monitor plant diseases that often infect the plants, and yet we need more food to feed more than 7 billion people globally. But what is that they are still getting useless of over 50%, and this is attributed to diseases. And well, the best pest management practice is to first identify a disease correctly, and this is the crucial step because this helps the farmer to identify the right pesticides that can be applied on the crop as well as the best management practices to see that the pest doesn't affect the yield and the crop health. Well, the existing disease identification approaches that are available now, such as using agriculture extension institutions, which offer local plant clinics that help farmers with knowledge of how to treat the diseases and how to apply the pesticide, and also farmers that have good knowledge of the internet and smartphones, and maybe those that have internet, have computers, can use internet to try to compare the symptoms of the diseases that they are seeing on their farm, and then try to read them online to see if there's a correlation between the symptoms and which tests are used to treat such diseases. Well, due to the fast-paced advances in global smartphone use, we believe there is an opportunity to use deep learning smartphone as deep diagnosis because the current smartphones have high computing power, resolution displays, extensive built-in set of accessories, the HD cameras, and this gives the smartphone as the best suit for deep learning. So far, the deep convolution networks that have been developed can classify images of about 100 possible categories with minimum error rate between 16.4 and to 3.4, and this is reported by the authors of this paper. So where I went to the internet and then came across these pictures, and then I pose a question to you, and maybe you're thinking that just imagine of a situation whereby a farmer has a phone and iPad, and this farmer can easily identify a disease that has attacked the crops, and he can be able to find a solution and apply the right pesticide on the crop. Well, on my left here, you can see I got this photo from one of the ongoing research that is they're trying to pilot study a research in Tanzania using a smartphone approach to detect diseases. Um, so far as this current research on disease diagnosis, which I've just talked about, so it is spearheaded by David Hughes, who is uh, one of the authors of this paper, and then James Lay. So if you want to read about this article, you can go to the resource that I put down here. But then there's one eye-catching statement that I got from this article. They say that smartphones are becoming more and more common in Middle Africa, explained by the project leaders. Uh, they say that as smallholders or extension officers with a best smartphone with a camera will be able to download the app, fire it up, point it at a link with disease symptoms and get an initial diagnosis. And that is true reversionary. So they're trying to test this app to see if it can really identify the diseases that always attack the cassava. So let's see what they'll get from their research. Well, if we go back to our paper, so we know large neural networks are time consuming during the training of this network to really be able to classify images and be able to get used to the data that is being input into the neural network. But once it is trained, then it can quickly classify the images. That makes it a good candidate for consumer applications in smartphones. When we know these neural networks are simply mapping the input can be the image of the plant, the output layer, which is the crop disease layer. So if you have the crop and then you have a disease, then you can really be able to see, to identify that disease and be able to be able to treat the disease. So, but the main challenge is, as we all know, that building a network structure that correctly map the input to output is challenging, mainly during the tuning of parameters and also during the training, and as well as testing the model to see if it is working with the data set. And also finding a large and verified data set of images of disease and health plants taken at the right orientation to develop accurate image classifier can also be a challenge. Well, what was the main motive of this research? Well, it was to develop accurate image classifier for the purposes of plant disease diagnosis using image data set to develop a well-trained model with the ability to predict correct crop disease pair. And specifically, they are trying to classify crop diseases in different crop species using a convolutional neural network approach to come up with possible classes. And the second specific objective was to focus on how the developed network can be used in a smartphone for plant disease diagnosis. Well, let's go to the data description that were used in this research. So these researchers used a data set from what they call the Plant Village Project. And this data set had over 54,306 images of plant leaves and 38 labels. So when you look at the right we have different labels that show different leaves of different crop species. Um, so the plant species that were used, let's say we have apple. So this leaf 4 with label 4, it is a, apple. It is an apple leaf, but healthy. And then we can have corn, and then there is strawberry, which is 27. So all different labels depict if the crop was healthy or if the crop was was if the crop had a disease that is shown by the spots we see. If you see the spots, this is a particular disease that agronomists can be able to identify or transcend. Well, they went ahead and they divided up the different uh, different leaves uh, into different versions or into different scales. We had the original, which is the colored, and then they had another one that was grayscale, so they turned this leaf into gray, and also they did the segmentation to remove the background information that could bring bias in the data set. Then after they resized each image to 256 by 256 pixels, and these downscaled images were used as input for model optimization and prediction. The model approaches that were used are two popular convolutional network architecture. One of them was AlexNet and the other one was GoogleNet. Just to give a brief description of the AlexNet, it just has a stack of uh, convolutional layers. Most times it is 5 in number, and then a fully connected layer, which are 3 in number, and then it ends with a softmax layer. But the two convolutional layers, the first two convolutional layers are followed by normalization, and then a pooling layer, and the last convolution, which is 5, is followed by a single pooling layer. Finally, the connected layer before a softmax layer, it has 38 outputs, which the labels we have seen in the data set, and feeds this in the softmax layer. But then the softmax layer goes ahead and normalizes the input from the fully connected layer uh, to have a distribution of 38 classes to add up to 1, and all the 7 layers have a linear activation. This linear activation just converts the linearity of the model into a nonlinear format. But then the last two fully connected layers have a dropout ratio, 4.5. Then looking at the GoogleNet, it is just a deep and wide architecture with 22 layers, but we have to note that it has fewer parameters compared to AlexNet. It just uses the 1 by 2, 3 by 3, and 5 by 5 convolution with max pooling in parallel so that the dimensions of the images are reduced. And also it has a filter concatenation layer that concatenates the output of all 5 layers. So concatenates the wireless input. Maybe it combines all the outputs into one output layer. And then they went ahead and performed, they evaluated the model using the image data set that I talked about, and then to see if maybe the model was overfitting in any of the train test set splits. So the data set was split into train test sets, and they made sure that the images of the same leaf contained either training or testing set. So the training test splits were 80 to 20, and 80 was referred to the whole data set used for training, 80% of the whole data set used for training, and 20% for testing. So what you see, the first is the training data set that was used, and then the second is the data set that was used for testing. And they went ahead and then determined the mean precision, mean score, and mean F1 score to check the model accuracy at regular intervals at the end or at the end of every epoch. So epoch is just the number of times through which the input goes through the network. So they did the model training using two approaches. One of them is train the model from scratch, and then transfer learning. So transfer learning generally, they picked a model that previously used to classify maybe objects, but not necessarily looking at crop disease like crop disease classification. So then they try to also to fine tune the model and then put in the data set that had crop diseases to see how the model performs. So as I've said, transfer learning just exports large amount of vision knowledge already landing pre-trained AlexNet and VideoNet models. So these models can be downloaded from internet. And then the model was, the parameters within the model were tuned using the solvent type used was stochastic gradient descent, and the base learning was 0.05. The learning rate policy was step, and this decreased by a factor of 10 for every, I think for every epoch. And the momentum used was 0.9, and the weight decay was 0.005, and the gamma was 0.1, and the batch size for the Google Net was 24, and for the AlexNet was 100. So let's go to results. So doing the random guessing on the data set, they come up with the average accuracy of 2.63%. And from the different experiment configurations using the aid of the model approach, and then the type of the training used, and then the image type used, and the train test set used. For the AlexNet, when they use training from scratch and the grayscale image, they came up with an approach of an accuracy of 85.3%. And then for GoogleNet, using the transfer learning with the card image and using this train test set, they came up with an approach of 99.34%. So generally, the GoogleNet performed better in terms of overfitting when they're checking the overfitting with variation of test to training ratios. So this configuration gave an accuracy of 98.21%. So looking at these figures, figure A just shows us they try to compare the model accuracy using the two model approaches they used. We had AlexNet and GoogleNet. The green line shows the performance of GoogleNet, and the blue shows the performance of AlexNet. From this figure, we can see that almost the mean F1 score of GoogleNet was almost approaching 1, and then for the AlexNet was about 0.95. So generally, from figure A, we can depict that GoogleNet architecture performs better than AlexNet. And then figure B, we had to compare the two methods used for training the model, aid of the models, using the fine tuning. This is the same as the transfer learning, and then train from scratch. You can see that fine tuning, the training, like transfer learning, it performs better than trained from scratch. So, in conclusion, the transfer learning as a method of training always provides better results, as shown in figure 3B. And then they went ahead and looked at the loss, the training loss with the test data set, and then, sorry, and then the loss with the training data set. And they realized that there was no big difference of variability between the two. They almost had the same trend and almost had the same losses. So in general, there was no difference between validation and training loss, confirming that overfitting didn't influence the results. Then in figure D, they went ahead and then tested different sets that were used, the train test sets that were used, the 20 and 80, 40, 60, 50, 50, 60, 40, and 820. And from this, they realized that the train set that had 8% of the whole data set used for training and 20% used for testing performed better than other sets. So from that figure 3D, we can say that the performance of AlexNet and GoogleNet degrade when test to train set ratio is increased. So let's say, because this was our test and this was our train, so if we had this as the fact, so if you keep on increasing the test to train set, then you're going to lose the accuracy of the model. Then the last graph is showing us how the different versions of images had an influence on the accuracy of the model. So we can see the color, which is the blue, almost had the F1 score that is close to 1, and then the segmented was in between, and then the gray was the one which didn't perform better. So from this graph, we can see that there's a difference in performance of the model when different versions of images are used, and then the model performs better with curved vision, followed by segmented, and poor with grayscale version, as I explained earlier. So from this research, we came to a conclusion that for sure the convolutional neural networks, they have ability to classify images and can be used in plant disease identification. And also, the model trained on images of plant leaves performed well with a top accuracy of 99.25%, and it can be applied in smartphones to diagnose diseases in plants. But however, the model has some limitations. So they're saying the limitations can be testing the same model with images taken under different conditions. So different conditions here, they are referring to if you're using a different data set, maybe collected by different, like from different conditions and different areas, we might actually reduce the accuracy to near 31%. You can imagine from 99 to 31%. So there's still a challenge in how images can be collected and which conditions can really give us good images that try to give us a high accuracy. The second one is that for this model, they trained the model with single leaves. As you have seen, I showed you their leaves and labels. So they are trying to use a single leaf as an input into the neural network and then trying to come up with a classification. So training a model training, the training model classified single leaves facing up and in a homogeneous background. But in reality, we have the farmer has to take the leaf images as they attach on the plant to identify the confusing feature. So there's still a challenge. They don't know if really the model can be able to identify a disease if a farmer has a smartphone that the farmer takes an image instantly on the leaf that is attached to the plant. If we get the same results as this model provided. Thank you, and I welcome questions now. Are you there?
Hello, Abia. You
Yes,
can still hear us, right? Can you still hear us?
yes, I'm seeing you.
Okay.
Yeah.
I'll have space for you.
So, any questions from the presentation?
Are there any questions? This is a very agricultural oriented project. It's about classifying the leaf, the species from the leaves. So Abia, I have a question. Is this paper all done about classifying the species?
Yes.
The 38 classes you have?
Yeah.
That's what they do. They actually did not care about the plant disease yet, right? Is it?
For the classification, they are trying to classify a plant, a crop species with a disease. So that pair is the classification they are trying to look at. A crop type, and then a disease type.
Yeah, but did their results show any of the disease classification at all?
No, they stopped uh, at, like training. They stopped at testing the model and seeing the model like evaluating the model accuracy and performance.
Okay. Well, I will let the students here to see if they have any questions. Josh, I will make you ask a question because you're in agriculture. Yeah, so the question here by a student, Abia, is if they combine the species with the disease, what would be the outcome or the accuracy rate of this methodology?
That's a challenging question.
Did the paper talk about it at all? Because I think
No, they didn't talk about it. They're just trying to see if the model can be able to can be used to predict a crop disease pair.
Okay.
But then they didn't go deep into identifying using image to predict a disease on a crop species.
Yeah, they didn't do that, did they?
Yeah, they didn't do that.
They didn't.
Yeah.
Okay.
Yeah. But that's why I'm now trying to test. I think they came up, they found ways of how to incorporate into a smartphone. So that's why I think that in Tanzania trying to test to see if it can work in a real life situation.
Yeah.
Yeah. Yeah.
So I wonder, anybody here, have we got any expertise here that they can program with smartphone? Nobody? You? A little bit? So what language you're using?
For Android, a lot of times.
Java?
For Apple, it's Yeah, sort of quick.
Okay.
You let and see your objects.
Right. So what's the application that you're writing?
I've just read simple application for
Okay.
nothing too crazy.
Yeah. Do you know how they different from like Arduino based programming? Is it quite similar? I mean, I guess the logical wise, it's quite similar, right, for all the programming. But the
So
specific syntax might be.
we've never done object-oriented programming. It's probably pretty similar to that.
Okay.
If we've done Java or C Sharp, Python has some object-oriented and MATLAB as well, but it's decent.
Okay. Yeah. Any questions? Yes.
Thinking about this whole set of reviews by the images, I'm wondering, in order for this project to be successful, are they going to also need to know and classify the leaves of normal plants which are not happy? So that like, the model can know the plant leaves are happy disease or not.
Yeah, so Abia, one question here from a student. He is wondering if you will have to feed the model with the healthy plant leaves as well, so that the model actually can tell this is a healthy leaf versus this is diseased leaf.
Yeah, true. They had the data set also contained the health plants. So if you see number 4, this is the apple leaf, and then they had the health plants, and then leaves that were depicting like diseases. So they had health plants also in the data. So if we see the cone number 10, and then you have diseases that attack the cone, so number 9 is in. So they had different sets of data that contain health plants as well.
So Ben, you're gonna say something? Stops. Yeah. Okay.
I just read the a little bit of the discussion they say.
Okay. All right. So Abia, can you scroll down to the training curve that you show us?
Okay.
I have found those are quite interesting to see.
So the
You have a family of curves that shows the training process and the validation process. Yeah, there you go.
yeah, so the first one, they compared the two model approaches using the AlexNet and then the Google model.
Yeah.
And
So
then,
what happens after 10 epochs? Seems like there is. So with this curve, does that mean that you actually just need to train them
so
like 12, 13 times?
So in the discussion, they said they realized that at 30 epochs, the curves they are trying to converge at the same value, F1 score. So that's why they stopped at 30.
That's why they choose the 30.
Yeah, because at 30, every curve was converging at the same value, like almost the same value. So
Yeah, because it's probably the changing of those parameters from epoch to epoch become really small, right? After you train them 12, it looks like the 11, 12 third epochs, right?
yeah.
Okay, and then on B, so that the blue curve, you say fine tuning, that is actually learning transfer, is it right?
I beg your pardon?
So on panel B,
Yeah, B.
we have a blue family of curve
Yeah,
labeled fine tuning.
yeah.
And I wonder what's the meaning of fine tuning? Is that learning transfer?
Yeah, they're referring to transfer learning. I think, yeah, because they're trying to actually then compare that two trainings that they use.
Okay.
Yeah.
So what is the original? Is it a Google Net transfer?
The original,
Is that the original Google Net that is transferred from?
yes.
Okay. So which means if you don't even change any parameters with the neural network, you can still get 90, or that's F1 score. That's still significantly higher than random, right? Random initialization.
Mm.
That was amazing. So do they discuss any of this point? Like, seems like the Google Net can be transferred to this particular sets.
Um, I'm not
I guess
sure.
what I'm interested in is there anything particular in Google Net that already somehow maybe this particular data set is a subset of the Google Net, then it's not surprising that because it's trained on that, then you already have a good performance. But if it isn't, then if let's say it doesn't have a lot of leaf examples at all in Google Net, then this kind of performance is
Yeah,
kind of interesting, right?
yeah, maybe.
Okay, well, so I'm just curious. Okay,
I
so
think they are trained the Google Net mode on the same. I don't know. It can be a different data set, but it might have had maybe same images
yeah,
as used
yeah,
data set.
yeah. I'm sure I think I know that the Google Net is trained on like tens of thousands of images on like 1,000 categories.
Mm.
So, but I doubt those 1,000 category would include like 38 of these leaves examples, right?
Yeah.
Very less likely. Yeah. Okay, can you go forward like the next slide?
Okay. That one.
Yeah. Okay, losses. Okay, so this is not surprising, right? So 2080 is the lowest and 8020 is the highest. Okay. All right. So it goes down. All right, and this is not surprising either, right? You should have your color information. If you include the color information, highest performance, and then segmentation help with the. It does not did not do as good as the color version, but it's better than grayscale.
Yeah.
Okay. Okay. All right. So, any about this presentation, that should be pretty straightforward. I guess this is one of those early, deep learning applications in agriculture. Usually when you publish, you really want to kind of be the number one to publish in that field. I think this article has been published 2016 or 2017, right?
Yeah. 2016.
2017?
Yeah, 2017.
Okay, yeah, it has been cited like 16, yeah. It has been cited like 100 times already.
Yeah.
It really wants to be the first one to do stuff like that.
Yeah.
Okay, so any other questions? No? All right, well, Abia, there's no more questions here. Well, thank you very much. Yeah, so I guess stay warm and we'll see you all next week.
Okay.
Okay?
All right.
Bye.
Bye.